Okay, so thank you very much, Matt. I realized a little bit too late that this is Cambridge, so the title should be From Newton to JWST. My name is Jan Scholtz. I'm a postdoc at Kavli. I work on supermassive black holes, how they influence the life of galaxies. But today, I'm not going to talk any of that. More, we are going to talk about how do we actually do what we do, because we don't use, smaller refractor telescopes. So I thought it's like as a warm-up, let's kind of address a few questions that I would like to address today. So first of all, how many modern research telescopes have an actual eyepiece? Like where you can go and look through it. Is it all of them? Is it none of them? It's actually a trick question. There's one. It's the Subaru telescope. It's an 8-meter telescope in Hawaii. And the reason why they put an eyepiece there is because when the Japanese emperor wanted to visit, they were like, well, the emperor has to look through the telescope. So they put an eyepiece. I think they used it in the 1990s, and ever since they actually haven't used it. What is the primary purpose of a telescope? Is it to magnify the sky? Is it to make sharp images? Is it anything else? Exactly. So this is one big sort of a misconception about telescopes is that, oh, it's about magnifying the images. No. Actually, the magnifications of telescopes, even if we can measure them, which is kind of hard when you go to CCDs, but it's about collecting light. It's about having as big buckets as possible. Now, how many colors do we use? As humans, we use 3, RGB, or close-ish to RGB. But we know that there are many more colors. How many do we do? It's another quick question that I'm going to show you. It's all of them. If you give an astronomer a different color, we will use them. It's extra data. It's extra information. So why do we need larger and larger telescopes? Why there is this obsession in astronomy to just go big? Is it because our egos? Yes, but not just that. It's because distant galaxies are incredibly faint. The amount of light, I was trying to calculate it, turned out to be relatively hard, but if you would, for example, look at all the light we collected in radio frequencies since 1950s, it would equal the energy of a snowflake landing on your skin. That's how little energy we have collected for the past 70 years. And that's, okay, you might say, it's just one band's radio, but actually, yeah. So we need collect as many photons as possible. Bigger telescopes means bigger buckets. You can think about it as in a rain. If you have a wider bucket, you're going to collect way more rainwater. And this is the only slide that will have any piece of maths on it, I promise. The surface area or the collecting area goes as the radius squared. So if you double the size of your telescope, you quadruple your collecting area, which is a huge help. That's why we are going from 1 meter to 2 meter to 10 meter these days. And in the future, we are thinking about a 40-meter telescope. Bigger telescope also means sharper images, because this is the last equation, I promise. The sigma, or like the thing on the left, it actually shows you sort of what is the distance between objects that you can recognize on the sky. It's some weird constant. This is the color of your light. And then this is the size of the telescope. So bigger the size of the telescope, the smaller details you can actually recognize. That goes linearly, which means that if you double the size of the telescope, the image is going to be twice as sharp, but it's still useful. Every single piece of sharpness actually really helps. So, at the beginnings, actually it wasn't Galileo Galilei that actually invented or kind of looked at it officially. It was Hans Lipsche in Netherlands in 1608. He actually, submitted a patent. It got never accepted. So Galileo Galilei improved the design in 1609, and we now kind of, it's like, look, first working telescope. This is actually it. You can see the replica in Florence, in the Galileo Galilei Museum. If you haven't been, you should definitely go, not because Florence has amazing food, but also this museum is absolutely spectacular, full of amazing stuff. The first reflecting telescope using mirror was in 1668. That was by Newton. So that's why Newton didn't do the first telescope. He did the first reflecting telescope. this is it. You can actually buy these replicas, by the way. I think this is the original, but you can actually get the replicas or sort of a small working desktop telescope. The way we normally look about these is that you have a lens, the lens focuses light, then you have an eyepiece that kind of just makes it, happy, available for the eye. And this is great. This is how everybody, if you Google a cartoon of a telescope, you will get essentially that. Problem is that, we don't do them anymore. This is the largest reflecting telescope we were able to do. It's in Yerkes Observatory in the US. The lens, which is right there on the top, is 1 meter in diameter. And it's 102 centimeters. The focal length, which means that the distance of this tube is roughly 19 meters. And the lens weighs 225 kilos. It's an absolute massive. The thing is, refracting telescopes, the one with lenses, I'm terribly sorry, but are not great. They just aren't. It's just limitations. And the first one is you're using a lens to focus your light. The problem is that the way it focuses light for a lens, it depends on the color. And it actually focuses different colors into different spots, which means you ended up with a little beautiful rainbow fuzzy image that's completely useless for astronomers. So we don't actually, the way you can do it and the way you can do them in cameras these days is that you use actually multiple lenses, all from a slightly different type of glass, and they correct each other along the way. But if you're doing a 1 meter lenses, you don't want to do 10 of them, 20 of them. They're going to be each 220 kilos. And the second bit, lenses bend because you can only support them from the outside. You can't just like poke their little stick and be like, okay, I don't want them to sag, right? It's a huge problem. And then you just end up with a big fuzzy image because your telescope is no longer actually focusing. Every single time you move your telescope, you have to refocus it completely from the scratch. And then you really, really hope that the wind is not going to move it again. So you move to mirrors, and then mirrors you can say, it's like, yeah, but do they really focus light? Well, they do, if they are in the right shape. So this is a parabolic mirror. This is actually the original design of Newton's telescope, where you have star light coming in, reflecting into a secondary, and that will go into your eyepiece. You kind of look through over here, or you put camera over here. And you can support them from underneath so they don't necessarily bend. The other one is that they reflect light exactly the same regardless of what is the color of it, except for X-rays, but we'll talk about them later. And there are no serious problems with them, which is very rare in astronomy because usually it's pros and cons everywhere. So you need to make a mirror. And the other one is that you can actually cast it relatively okay, even a 10-meter mirror. What you actually do is you fill a furnace full of glass, you melt it, and then you spin the furnace. And it's exactly like when you are mixing your tea with a spoon, it creates a parabola. And then you turn off the heating, and you wait about 3 months, because it's a 50 tons of glass, and you can't cool it quickly, otherwise it's going to crack. And at the end, you have actually, at the end, you don't have this. At the end, you have something that looks like this, but you then have to spend another 1.5 years of polishing it to this famous sort of number, which is your wavelength divided by 10, which in optical means roughly 50 nanometers. And I don't know how of a fraction of a hair strand it is, but I would say less than 100. So these are incredibly, but you end up with, in this case, 8-meter mirror, beautiful, with a hole in the middle, because that's where the light is actually reflecting back through, and there is a person in the scale for this one. They are huge. These are 8-meter class. The problem is that at some point we realized that they're actually becoming too big, and casting an 8-meter mirror that weighs 50, 60 tons is becoming a bit of a challenge. So we started using segments for your mirror. So these are hexagonal segments. This is on a Keck observatory. And now you have to make sure that they actually all act like a single piece of mirror. So what you do is that you put little pistons underneath, and these pistons actually move the segments every two times per second. They actually check whether they're still behaving like a perfect single mirror, check whether they are working, and then adjust if it's not working. By the way, the changes that you are doing with these pistons They are about 10 nanometers. So they are less than a millionth of a meter, almost close to a millionth of a millimeter. So these are tiny changes, but you need to make sure that these changes are happening in order for them to act like a single mirror. And this, you will see later, will now enable us to one day build a telescope that is 40 meters in diameter. Okay. Problem that we have is that atmosphere is really annoying, actually. If you ask an astronomer what are the biggest enemies of their work, they will say atmosphere. It doesn't matter what wavelength they are talking about, it's always going to be an atmosphere because it absorbs light. It doesn't look like it absorbs much in terms of in optical, but when you go to near infrared, water starts to absorb tons of light. If you go to X-rays, you cannot observe X-rays from ground-based. You actually have to go into space, which is great for life because then we don't get cancer, but on the other hand, it really sucks if you're an astronomer. But the thing is that these are not clouds, actually, because the last thing that the atmosphere is actually being uniform. It's not single pressure. It's not a single temperature. There are tiny little pockets of air that have slightly different temperature and pressure, which means they have a tiny different density. And if you have a tiny different density, it's like when light goes through air into water and you see that it bends. And exactly the same thing happens. They essentially act like tiny little unfocused lenses. So then the star does this. It does a little dance. It's what we say, the stars are twinkling. Everybody thinks it's romantic. If you ask an astronomer, we think it's annoying. It actually gets to so much point that once you reach about 1 meter telescope in diameter, there is no point in making the telescope bigger to get a sharper image because the atmosphere is always going to blur out your image. So we only build the telescopes bigger and bigger because we want to collect more light, not necessarily because we want to get the images sharper. We can't, the atmosphere is limiting, which is why you are wondering why we are building a 1.5 billion euro telescope in the southern hemisphere. And the reason is that there is something called adaptive optics. Also, the famous picture of having lasers from your telescope. And it's actually really clever because what we are doing is we are creating an artificial star in the atmosphere. So we are shooting a laser roughly 90 kilometers up, where I think that's officially classified as actually not being in our atmosphere. I think the Kármán line is about 75, 80 kilometers, so this is above it. But there's sodium in it, and you can actually ionize the sodium, you can excite the sodium, and then create an artificial star. And this is going to be now a video by Roller Observatory. You essentially take all of that light that comes from that artificial star, you figure out what distortion, what the dance is doing. This is what we call the wavefront, and you create a counter to it. It's essentially noise-canceling headphones, but for light. And then you have a tiny deformable mirror with little magnets underneath that are changing the shape of the mirror roughly 1,000 times a second to counteract the atmosphere. So this way, we are able to create essentially noise-canceling headphones, but for our telescopes. And it works really cool. You can actually get to the point where you can actually go correct the atmosphere, and you can get to the limit of your telescope and to the limit of your mirror, which sometimes you might call that we got to the diffraction limit of our telescope, which means that we are actually to the limit of the mirror again. These things were designed roughly I think the original idea came in the 70s, 80s, but we didn't have the computational power to actually do this in real times, 1,000 times per second until roughly 1990s, end of 1990s, where we did first prototypes, and now it's essentially on every single big observatory. The alternative, of course, you can launch it to space, which if it's Euclid, it will cost you, which is this one, it will cost you about $2 billion. And if it's this one, which is JWST, it will cost you about $12.5 billion. But I work on JWST, so I think it was worth it. So, okay, you spend all of this, you spend $12 billion on a telescope in space. So the images that you get from them must be really, really cool, right? I mean, this is what all the press releases are about. This is what we are selling to public. Well, the tiny problem is that, yeah, they are at the end, but this is usually the first images we get. And you were kind of like, what the hell? And that's because the telescopes are not perfect. The huge part is what we call the data reduction or data calibration. And there are tons and tons of things that we have to actually deal with. The first one is something called the flat fielding. So we used, actually JWST no longer uses CCDs, but it's CCD-like, so something that's in your phone as well, or in any of your cameras. But the thing is that what we call the response of the detector of the CCD is not the same on every single pixel. So sometimes the way you measure the light is actually you get a photon or light. It will hit your detector, your CCD, your pixel, and that one will just kind of pop out a few electrons. And then you just measure the current that the electrons that are there. Which is great, except every pixel is just not the same, and they are responding slightly different to the photon. So sometimes they launch 3 electrons, sometimes they just launch 2. Sometimes you have dead pixels that just do nothing, or they just, do current all the time. So you actually have to kind of get the response, and this is JWST response, by the way, from the CCD. And you would think for something that you spent $12 billion that it would have a better detector. This is way better than we originally thought it would. This is excellent. By the way, the scales is between 0.9 and 1.1, so it's roughly, these fluctuations are plus or minus 10%. You have to do a background subtraction, and it turns out background is essentially any lights that you have in the detector that is not actually caused necessarily by your astronomical objects. So in JWST, our biggest problem is actually the source of the background is actually it's the reflection of sunlight from the dust particles in the solar system. Because the sun, there is a tons of dust in our solar system. The sun illuminates it, the dust just reflects it, and it's like a sparkle essentially, and it's everywhere you look. As if you look out of the disk of the solar system, it's a little bit better, but they're still huge. So you need to essentially remove it by subtracting it. This is sometimes essentially the way we do it is that either we can estimate it directly from the images, and sometimes for some especially in near infrared, what we have to do is that we have to look at a star, and then we look at our object, our galaxy, and then we look at an empty patch of sky for the same duration. And then we look back, and then that's essentially our estimation of background that we had to subtract. So when you spent, I spent 6 hours on observing this galaxy, 2 hours I was staring at absolutely nothing, because I needed all of that to make my scientific data, the actual images of the galaxy, usable. Otherwise, it's just a nightmare. And then once in a while, we just have to do a good old visual inspection of everything. So I will talk about this type of data. These are not images. This is spectroscopy. This is integral field spectroscopy. You don't have to necessarily understand exactly what's happening. But can you see all of these white dots everywhere? Loads of them are automatically masked by our programs. We can actually do these automatically. One person especially here, Francesco Deogino, is an absolute legend when it comes to writing the programs that actually do it automatically. And then Hannah Ubler here, Dr. Hannah Ubler, is amazing as well. But sometimes you just have to kind of go and you have to draw these little ellipses, these little circles, these magenta, and just say, it's like, okay, that wasn't flagged properly. This is a cosmic ray, also high energy particle hitting the telescope and just, creating an artifact. And I don't want any artifacts. And then you repeat it for about 15 different exposures, because you never do one big, long integration or exposure on your target. You do about 15 shorter ones, if you're lucky and you've got so much time. Then you do it across many different colors. You add them all together. You then sort of assign them to different R and G and B parts of the images, and then you can finally create an image like this. So it takes a while. One other part that I wanted to talk to you about spectroscopy, but before we can do spectroscopy, we should talk about light spectrum and essentially the entire electromagnetic radiation. So this is a classical, image of a rainbow. This is the visible light. It's right here. We are actually seeing incredibly narrow part of electromagnetic spectrum. It's really depressing. You have UV. This is the one that gives you a tan and also cancer. This is the X-rays and gamma rays. X-rays are used for X-rays of your broken bones. Also give you cancer. The same for gamma rays. No, gamma rays are not going to turn you into Hulk. Then you have infrared, also known as the heat radiation. That's just light. Then you have radar, or the radio waves. They are just light, just different wavelength, but they are essentially light. The thing is that, if we would just have a human eye, you would have 3 colors. This is the image of a galaxy. This is sort of an example. And what you can start playing is that you can plot the different colors as sort of how bright they are in different colors. And you want as much information to reveal about what is happening with the galaxy. So you start adding additional point and another one and another one and another one. And then you can see that it starts to having a shape. And then you can write very complex computer codes that will essentially model all of these 6 different points, and you will get how heavy the galaxy is, how many stars is forming currently. But you are essentially limited to all of your knowledge about that galaxy, limited to about 7 points, I think, 6 points that I put on this. So what would be really cool, and also for each of these, you have to spend around 12 hours on the target. Just do 12 hours with one sort of color wheel on your detector. Then change the wheel, change it to a different color filter, do another one. So it takes tons and tons of time. So one other way of doing it is that you can do it with something called a spectrograph. This is a prism. You take your light source, you take it through a little triangle piece of glass. It's usually glass. And then you get a beautiful rainbow, and essentially you disperse all of that white light into each individual colors. You can also do it with something called a grating, and grating is essentially just something that has tiny little grooves, about 1,000 per millimeter. It's very tight. You can actually see a very, very rudimentary grating is a CD. If you turn the CD upside down and put it against the light, you can see that it disperses into a rainbow. It's just a rudimentary grating with really bad reflectivity. But there are tons of tutorials online how to build a spectrograph out of a CD. So you do that, you disperse it, and you get a spectrum. And now, this is my point, is how many colors do we use? Well, it's not 12. It's infinite number of colors. We will take every single color, and you will see that there is this is the overall shape. We call that continuum. It comes from the stars. You can figure out how many old stars there are, how many young stars there are in the galaxy. All of these peaks, we call them emission lines. The emission lines comes from different transitions from the different ionized atoms in the galaxy. This is, for example, oxygen, doubly ionized, called oxygen 3. This is hydrogen. This is another hydrogen, another oxygen. I think there's a carbon here somewhere. Right next to it is nitrogen, sulfur, and you can start doing I wonder how many metals there are. By the way, astronomers are incredibly lazy. Any element that is heavier than helium is a metal. So please, chemists in the audience, don't kill me. It's just easier, right? Because only helium and hydrogen was actually created in the Big Bang. Everything else was created in stars. So we just call it a metal, and it's easier. It just simplifies things. So can you actually do images with spectroscopy? And the question is, not really actually, but yes. So usually what we do is that we put the spectrograph on a single galaxy. So you combine all of the light. The other times we can do something called a multi-object spectrograph, which I'm going to just came over, where you just take 1,000 different spectra of 1,000 different galaxies, but they are combined. And then you have integral field spectrographs, also called IFUs. They are my favorite, so I just had to include them. And essentially what you do is that you have these tiny little slicers. And the slicers will first split the light into individual rows, and then the rows into individual pixels. So at the end, what you get is a cube. It's not an image. It's not a 2D image. It's a 3D image, where this is your position on the sky, just as you would look at it. And this is your wavelength or your color. And then every single pixel is a spectrum. And that is extremely time-demanding way of observing galaxies. You need about 7 hours with JWST to actually get a decent data cube. It's perfect. It's by the way, the data that I showed you for masking, that was actually from an IFU, and that's why they were in stripes, because every single stripe was one spectrum, or was going to be a spectrum once we actually cleaned it up. I just couldn't resist putting this one. I don't expect you to know. I'm not going to explain every single map. but you can essentially map, remember the emission lines, the little peaks? Well, now we can map every single one of them that are in the spectrum, and we know where the metals are, where in the galaxy. And then there is another thing, is that we can actually start playing a little bit, and we can actually measure the speeds and turbulence at every position in the galaxy, which actually is this row. So you can actually figure out, it's like, oh, this galaxy, about 700 million years after the Big Bang, it's nicely rotating. It's actually not, it's merging with another one, but this part is going towards you, this part is going away from you, so they are nicely rotating. And we can also do a little bit something more complicated. You can actually start decomposing the different emission lines, and then at the end, you actually get these outflows, and outflows are just massive galactic winds of roughly 600, 700 kilometers per second that are being driven by either exploding supernovae or supermassive black holes. Just one thing I wanted to stress is that the instruments are huge. So this is MUSE, it's an IFU. So that's the one that dices the light into each individual pixels, and then eventually give you a spectrum. And this is in Chile, and you can see that this is something that's like twice the size of a human. They weigh several tons. And this is actually, it's still not on a telescope. It's called MOONS. It's the multi-object spectrograph. The idea behind this one is that we will be able to take a spectrum of 1,000 galaxies at the same time. So the idea that we are leading, or my boss here is leading, is that one day we'll have a spectrum of 1 million galaxies at sort of midway through the age of the universe, which is something that has never been done before. And this is the walkway. It's a massive thing. It's cooled to roughly minus 200 degrees Celsius because heat is not good for us. But it's a huge thing. And yeah, I just wanted to, one thing is that while we're on optics, I'm going to be really quickly. How do you focus X-rays? So X-rays, like I pointed out, are light. But also, we both know that if you're hit by an X-ray, the X-ray will just go through you. So you ricochet them. You literally ricochet them like a bullet, where you just have these angled mirrors, and they just ricochet once, twice, and that's how you focus them onto some sort of a detector that you can do in X-ray. So essentially here you put a Geiger counter, just really, really, really advanced Geiger counter. This is NuSTAR. It was one of the first things because there's a little scissor lift in the telescope. So when they launched it into space, this one was actually this piece was right here. And then after the launch, it deployed, and it literally deployed a scissor lift to extend it, because you have this distance where you ricochet all of your X-rays. You can't graze them by big angles. So they take a long time to actually get into the focus. So future facilities, I would say we are always going bigger. This is ELT, the European Extremely Large Telescope. If you wonder why we called it Extremely Large Telescope, it's because our original idea, the Overwhelmingly Large Telescope, the OWL, turned out to be too big to build. So we had to build with only Extremely Large Telescope. It's the successor to Very Large Telescope. It's going to be bigger than Big Ben. It's a 40 meter in diameter. There's a huge generation of the next generation telescopes. By the way, Overwhelmingly Large Telescope canceled. I was not joking. They're actually trying to build it. It's 100 meter in diameter, but instead we are building this ELT. It's going to be probably finished 2030, 2028. You have JWST, and then you have the TMT. I have no idea what's going on that one because I was supposed to build it in Hawaii, but there are some problems with that. And then also the Giant Magellan Telescope. So, few things. Modern telescopes are enormous. We don't have eyepieces. We use really sensitive cameras. We are using as many colors as possible. The data that you get is rubbish at the beginning. Like, you really need, when you set up your programs and your code and you put it on a high performance server, it will take roughly 36 hours to get an image, because there are so many things that you have to do, and these images are huge. The telescopes they are essentially sort of light laboratories these days. They are not just a random DSLRs that you just put on a camera and be like, okay, done. And remember, it's not just visible light, and with it's X-rays, it's radio, it's infrared, we do everything. And lastly, yeah, even with them, we actually split them to millions and millions of colors to try to learn something about galaxies. So I hope you like this overview, and let me know if you have any questions.
Wonderful. Do we have any questions? Yes.
Thank you. This is really interesting. You mentioned that overwhelmingly large telescope is like too big to build. Can you tell us a little bit more about why that was?
Money. So ELT costs roughly 1.5 billion euros. The cost of a telescope doesn't scale linearly with the diameter, with the size of it. It goes, wait, so I think it was like 12 billion euros or 10 billion euros, which turned out to be too much. I can understand that. The biggest problem is that for example, of ELT, it's not going to work without adaptive optics, even to the atmosphere limited resolution. And the reason is that the sort of the size of the secondary mirror, if I somewhere find it where the secondary was, I have a picture of a secondary mirror. Which is this one. In case of ELT, it's 4 meters. And it's suspended about 60 meters above in the air, which means that wind is actually moving it. So you need to on-fly steer the secondary mirror so you always focus in the right. You cannot create a rigid structure that big. And it just turns out that all of these engineering challenges turn out to be just too big for a 100-meter telescope, where this would essentially be 3 times as big. So yeah, to go only 40 meters, but.
Where is the ELT?
So it's in Chile. So it's in Chile. It's actually right next to Cerro. There's a place called Paranal. It's roughly 50 kilometers from Antofagasta. It's 2,500 meters above sea level. And then, yeah, it's going to be right next to it. The VLT and the ELT are actually going to share the control room. And the ELT is going to be roughly 25 kilometers from their control room, but they just didn't want to build a completely new, setup and offices so close.
What would be the point of that, the ELT, the extra big one? Is it to make things finer or better pictures? Or
So it's just to collect more light. So
collect more light, so going further back? Sort of
So I don't think in terms of further back, it's not going to trump JWST. JWST is just uniquely designed for that. But there's going to be much better resolution, so you'll be able to see things in much better detail. We'll also be able to see things that are much fainter. So even within sort of, what I would call the relatively local, which is half of the age of the universe these days, you will actually be able to see, for example, individual star-forming regions in a galaxy. So you can start learning way more, not just taking a galaxy as this one blob, but you will be able to start learning about the individual components of the galaxy. This is going to be actually sensitive enough that for the exoplanets, it will actually be able to, what we call resolve out, or actually separate the star and the exoplanet, because right now they are just one merged blob, and we have to do very, very clever techniques. But here now we are actually going to be able to separate them. They might be able to see exomoons, so moons about planets around different stars. I'm a bit skeptical, but it's not my area of research, so maybe I shouldn't be. So yeah.
Cool. I think we'll make this last question, because I think the observers are ready for us outside. So please.
Sorry to keep everyone eager. What difference has the advances in software and stuff like AI has made for image processing?
Image processing, none. Image processing, not really simply. At some point, a robust statistics is quite a powerful technique. Where we can do is that with these new facilities, we're going to have million spectra. We are going to be for Euclid and these other large surveys, all sky surveys, we will have billions and billions of galaxies. So there we are looking into some ways of actually using AI in order to sort of analyze the data rather than actually reduce it. Unfortunately, the biggest problem with AI is that even if you train it, you can only train it on something that you know. And the whole point of these big surveys is trying to figure out what you don't know. So we'll see what, it has a future in astronomy. We'll see how big one and what it is.
Wonderful. Okay, so if you follow me, I will lead